All right, ladies and gentlemen, this class recording has begun. So, yesterday we started talking about this electricity unit, and the first thing we talked about was electric charge. Back on Wednesday, you guys did some reading from your book, and you filled out this graphic organizer about the similarities and differences between positive charge and negative charge. So to get us started for today, what I would like you to do is this. Grab your graphic organizer from Wednesday, grab your outline from yesterday, and see if there is anything that you need to change or if there's anything you need to include that you didn't previously on your graphic organizer based off of our discussion from yesterday. Yes, Ryan? Okay. No new reading, just kind of look over your graphic organizer, look over your outline, see if there's things you need to include or change about what you wrote. 1 minute, you can talk to the person next to you. Go. Seconds. All right. So, let's review. Underneath the similarities, or what they have in common, yesterday or Wednesday we wrote down a couple of things. Let's review some of them. So what do positive charge and negative charge have in common? Pretty good. They both come from subatomic particles, right? Lauren, go ahead. They attract each other, okay. Ryan, good. They are measured in coulombs. That might be something that you didn't write down originally on Wednesday, but we did talk about it yesterday. Pat, do you want to add something, or does somebody say yours? Okay. Lauren, good. They are, relatively speaking, the same amount of charge, right? Same amount of positive or negative, okay? Some things we might want to add. Yesterday, as opposed to talking about a single negative charge or a single positive charge, we talked about things that had positive charge and things that had negative charge. What do those have in common? An object that has a negative charge or has a positive charge. Well, that's where negative charges come from, but let's talk about an object that has a negative charge or an object that has a positive charge. Yes, we already established that. Lightning isn't formed of this, but how does something get a charge? What has to happen? Okay, go ahead. It has to end up with a different number of what? It has to end up with an imbalance of protons and electrons, right? Depending on which way we're imbalanced, that then can influence whether it becomes positive or whether it becomes negative, right? So, things that have positive charge and things that have negative charge have a different number of protons and electrons, or an imbalance of protons and electrons. What about some differences? Those are all similarities. What makes positive and negative charge different from one another, right?
Well, one thing that I added was an electron charge has negative 1.60 times 10 to the negative 9.4.
Okay.
And positive charges have positive 1.60 times 10 to the negative 9.
Okay, so yesterday we talked about the amount of charge, 1.6 times 10 to the minus 19 coulombs. they have the same amount of charge, but positive charge is obviously positive and negative charge is negative, or a positive. Protons have positive 1.6 times 10 to the minus 19 coulombs. Electrons have negative that amount, right? What else makes positive and negative charges different from one another? Good. Tell that from the name, yes. Right. Grady. Okay, so let's go more. Grady said protons are in the nucleus, but electrons are outside. Let's even back that up a little bit. Where do positive charges come from specifically? Well, which one of those has a positive charge? Protons, right? Positive charges come from protons. Negative charges come from electrons. And then they're located in different parts of the atom, all right? One thing that we talked about yesterday when we talk about an object that has a positive charge, right? How do we get things to have a positive charge or have a negative charge?
Well, you have to lose.
How do things get negative charges? No. There's more electrons than protons, but we get that by... How do we get... Hold on. So, something that has a negative charge has more electrons than protons, but how does that happen? No. Okay. In order to get more electrons than protons, you gain electrons. To get a positive charge when you have more protons than electrons, what has to happen? You lose electrons. You never gain or lose protons. Okay? So that's what they have, that makes them different, right? Positive charges have lost electrons. Negative charges have gained electrons. It's always a transfer of electrons, never protons. Okay? All right, good there? Yes, no, maybe. All right. Yesterday, towards the end of class, we didn't actually get done with this, but if you would please, open up your book to page 602. Page 602. All right, on page 602, down towards the bottom, actually about halfway down, there is a section that is labeled Static Electricity and Charging. To refresh our memories as far as what these different types of charging are, if you would please. I would like you to read that section that says static electricity and charging. So it's this paragraph at the beginning, charging by friction, charging by contact, and then up at the top of page 603, charging by induction. So let's read those 4 paragraphs. We'll come back and we'll discuss together. Go. All right, ladies and gentlemen, recording has started again. So, I paused the recording while you guys were reading because I didn't think I needed 5 minutes of just silence on the recording. So.
And then you would have heard us.
All right, that's why we did that while we paused. So. All right. Wednesday, I gave you 3 graphic organizers. We didn't get to all 3 of them. We only actually got to 1 of them. Let's pull this one out, the one that is like landscape across the page. And up at the top, it should say charging by friction, charging by contact, inducing a charge in a conductor. All right. Yesterday, sideways one, the one that says the landscape one, sideways. No, it doesn't, but I did say that. All right, so yesterday we started talking about these a little bit. Let's talk about similarities. What do all 3 methods of charging have in common? See, what's one thing? They all charge things. Good, all right. So, tell me good. Okay, there are a transfer of charges. Specifically, what kind of charges? What charges move around when we charge things? Electrons. So all of these methods of charging involve a transfer of electrons. Okay? Another important idea, right? As we move electrons around, if some object gains electrons, what has to happen somewhere else? Another object has to lose electrons. Pat, what do we call that idea? One object gains, one object loses, but what happens to the total amount of charge?
Stays the same.
Stays the same. What do we call that idea? Conservation of charge. When we are charging things, we must maintain conservation of charge. So one object may gain electrons, but another object will have to lose electrons. How many? How many compared to the object that gained electrons? The same, so that the total amount of charge remains the same. And that's the idea of conservation. Okay? That's conservation, right? Yeah. The statement of it is called the law, but the idea is conservation. All right. What makes them unique? So we said with friction, there has to be what?
Rubbing.
Let's go more generally with movement. All right? There has to be some kind of movement, right? Some kind of contact, some kind of movement, okay? And as those two surfaces move across each other, electrons are transferred from one to the other, okay? Charging by contact, right? There has to be what? Contact, right? There has to be touching. We said this sometimes also goes by the name of what? What did I call it in your outline yesterday? Conduction, right? Charging by conduction, right? Now, induction or inducing a charge in a conductor is a little tricky, right? And so let's take a look at the picture that's at the top of page 603 of this person touching a doorknob. Stephen, go ahead.
So, when he's about to touch it,
Yep.
the electrons move away because in his hand there's already electrons.
Okay.
And they repel each other, but since there's positive protons, they attract each other before they touch them.
Okay. So let's talk about, generally speaking, that was a good description. Let's talk about it here, okay? So, you slide your feet across the carpet, right? And charging by friction, your body gains a negative charge. You pick up electrons from the carpet, okay? Your hand, just a small portion of your body, right? Your hand has a negative charge. As the hand reaches towards the doorknob, because the electrons in the doorknob are repelled by the electrons in your hand, they all slide to the other side away from the negative charge of your hand. Is there an imbalance of electrons and protons here?
No.
Are they unbalanced?
No.
Yes. Is there, no, in the doorknob. Let's focus on the doorknob.
Oh.
Are the electrons and protons in the doorknob unbalanced?
No.
Yes.
Yes. Is there a different number of them, though? Does the doorknob have a net charge? That's a good question. Before you answer that question, what do you need to know? What's net charge, right? Well, what is net charge? Yes. True. But when you talk about net worth, right, you have to figure out how much money you make, but what else? How much money you have to spend, right? So it takes into account what you bring in and what you take out. So a net charge would be a different number of protons and electrons. Does the doorknob have a net charge? No. It's got 3 protons and 3 electrons. Obviously, there's way more than that in real life, but in this picture, you got 3 protons and 3 electrons. So charging by induction doesn't actually cause a net charge, but it does cause one part of the doorknob to act differently than another part of the doorknob. In essence, what have we done out of the doorknob? We've turned it into a what? Into a magnet, basically, right? Where one end behaves differently than the other end. But, and that's charging by induction. But have we actually created a net charge? No. Friction and conduction actually result in net charges. Objects have more or less electrons than protons. But in induction, that doesn't happen. All right? Now, let's say we broke the doorknob in half. Handle came off away from the door. Would there be a net charge then? In each section, yes, there would be. The part of the handle would have more protons than electrons. The part on the door would have more electrons than protons. But while it's together, technically there is no net charge. Does that make sense? All right, so that's why charging by induction is definitely a little different than the other two. Charging by induction does create an imbalance, but not technically a net charge. All right? Does that make sense? Okay. All right. Ronnie, go ahead. Net charge means that we have a different number of protons and electrons. Okay? So, Ronnie, are you familiar with the idea of a net profit? Okay. So, did I give you the lemonade stand example in class yesterday? I think in the other class I did, but all right. So let's say net profit, right? Let's say you want to have a lemonade stand over the summer, okay? And you go to your mom and say, "Mom, I want to have a lemonade stand." And she says, "Okay, you can use my lemonade mix, but you got to pay me back." Okay? So you use Mom's lemonade mix. You make a couple pitchers of lemonade. You go out, you sell it, and you make $25, which I know is kind of steep for what you usually make out of a lemonade stand, but whatever, right? So let's say you made $25 in lemonade sales. Is that your profit? No, because what do you have to do? You got to pay Mom back, right? So your net profit maybe is only $20 because you owed Mom $5 for lemonade mix, right? So we take in all the stuff that you have coming in and subtract all the stuff you have coming out. Same thing. That's the same thing with net worth, right? That's what. So Ronnie, when we talk about net charge, we have to count up all the electrons and all the protons and see if there's anything different, if they have a different number of them. Does that make sense? In an atom, we talked about that there's the same number of protons and electrons, right? So the net charge on the atom is 0 because there's just as many positives as there are negatives, right? But if we gain or lose electrons, now there won't be the same number of protons and electrons. So that object then would have a net charge. Either a net positive charge if it loses electrons, or a net negative charge if it gains electrons. Okay? All right, good. One type of charging that we talked about yesterday was grounding, right? Grounding is basically just charging by contact, but what are we charging by contact? Did we talk about grounding yesterday? We didn't get there? Okay. I thought we did. Okay. We did. Okay. So grounding means we're just transferring electrons where? To the Earth, right? And because the Earth is so big, it basically can take on electrons or give off electrons as much as we want. Okay. All right. Good there? All right. Let's go here. Okay. We learned yesterday, and you guys saw in your demonstrations that you did on Tuesday, like charges attract or repel each other, opposite charges attract each other. And that means we can make the water stream move if we take the rubber rod, and we rub it, or we charge by friction on the rabbit fur, right? then we take it by the water, it can make the water move, or we can pick up the little discs of paper or whatever. All right? That means that, oh, I should go here. That means that charges can apply forces to each other. Forces are what cause objects to change what they're doing. The water stream was falling straight down, but when you brought the rubber rod close to it, it bent. A force is required to do that. Those forces, in this case, come from the charges. They can either repel each other or they can attract each other. Jafar, go ahead. Water has a charge. It's more, though, Jafar, we'll see this when we get into bonding a little bit more. It's more like induction, where if you counted up all the total number of protons and electrons in water, it wouldn't be different. But where those protons and electrons are distributed causes it to behave as if it has a charge. So it's kind of like induction in that way. It's technically not charged, but the way the electrons are distributed in water makes it behave that way. Right? All right, so Coulomb's law describes for us the force that charges exert on one another. And you guys have this written down, right? F sub E equals QC, KC, Q1, Q2, goodness gracious, over D squared. All right, now, I have what all those things mean at the bottom, but let's talk about them more in what they do to the charge, okay? Q1 and Q2 are the value of the charges. We said, what's responsible for giving something a charge? What has to happen in order for it to have a net charge? An imbalance or a different number of protons and electrons, right? The Q values here describe for us how big of an imbalance there is between protons and electrons, right? Or what's the difference between the number of protons and the number of electrons? If you take the rubber rod and you rub it on the rabbit for 15 times, there will be an imbalance of protons and electrons. But if you rub it on the rabbit for 100 times, there's going to be an even bigger difference in the number of protons and electrons. How big of a difference there is between protons and electrons is what Q represents, or the amount of charge. And then D represents the distance, how far apart those charges are. Good with those so far? And then K is a constant value. It never changes. But more importantly than what these things are, let's talk about what they mean. This equation that shows us the amount of force, right? First it's an equation, meaning what has to be true about the two sides. They have to be equal. That's what an equation is. The right-hand side of this equation, though, is a fraction, right? And in essence, a fraction is a division problem. Yes? Okay? And that means the left-hand side of this equation is the answer to this division problem on the right-hand side. Good? All right. So, let's talk about Q. If we make the charge bigger, we are increasing the numerator of that fraction. If we make the numerator of a fraction bigger, what happens to the answer of that fraction? It gets bigger too, right? If you go from 1/5 of a pi to 2/5 of a pi to 3/5 of a pi, right? What's happening to the amount of pi you're getting? Right? More pi, right? So, if charge gets bigger, force gets bigger. What do we call that? What kind of relationship is that? One gets bigger, the other one gets bigger. What do we call that relationship? That is a direct relationship, right? One gets bigger, the other one gets bigger. So, force is directly related to the size of the charge. If we rub the rubber rod with the rabbit fur 15 times, there'll be a certain amount of force between the rod and the water stream, right? If we rub the rabbit fur 30 times, twice as much charge, how much force is there going to be? Twice as much.
So whatever you do, you
That's a direct relationship.
Law of conversation.
Kind of. But where is distance in this fraction?
distance between the charges.
It's in denominator. If we make the denominator bigger, what happens to the answer of that fraction? It gets smaller. 1/2, 1/3, 1/4, 1/5. How much of the pie are we talking about now? Less and less and less. So we call that what kind of a relationship? One gets bigger and the other one gets smaller. An inverse relationship. An inverse relationship. But there's something special about this inverse relationship. What are we doing to distance in this equation?
Squaring it.
You're squaring it. So if you, let's say you charge up the rubber rod with the rabbit fur and you hold it 1 inch away from the stream of water, and it will bend a certain amount. If you hold the rod 2 inches away, first, is the water going to bend more or less? Less, because we increase the distance. But is it going to bend half as much? No, it's going to bend how much? Not 4 times, but 1/4, because it's on the bottom, right? We refer to this as an inverse square relationship. Inverse square relationship. This is your first example of an inverse square relationship. Things get in the bottom, generally it's distance. Distance increases, the force decreases, but not by just as much, by that much squared. So going from 1 inch to 2 inches isn't half as much force, it's 1/4 as much force. 1/2 squared. If we move it 5 inches away, 1/25th the amount of force. 1/5 squared. So, here, Jafar, let's do this. Okay, picture. So, there's the stream of water that's coming out of the drain. Okay, here. Right, there's the sink, the little spigot on it, makes the water come out like that. Okay. All right, so here is the black rubber rod that you charged up, right? And okay, let's do this. Okay. There's your hand holding it. Yes. Okay. All right. So you rubbed it on the rabbit fur, and you gave it a bunch of negative charges, right? Yes, it looks like a loaf of bread. Right? It kind of looks like a baguette. You know?
Oh, it does.
But anyway, so it has a bunch of negative charges, and that makes the water. Oh. And that makes the water do this, right? It bends towards it, okay? All right, let's see if I can do this. Oh, that's not what I wanted to do. Oh. Okay. Just get that out of the way. Nah. Crud. This is here. Let me do this. This is a train wreck. I'm sorry.
Yeah, you're recording too.
It's alright. Alright. Oh yeah. Okay. Okay. Trevor, we ready?
Yeah.
All right. So, you bring the rubber rod close to the water, right? Let's say that this is, let's say that this is 1 inch away, okay? And the water stream is going to bend, let's say, this much, okay? If we move it this far, okay? Now we're 2 inches away, okay? It's not going to bend half as much. It's only going to bend 1/4 as much because it's 1/2 squared, okay? If we move this, five inches, right? Does that make sense so far? Okay. All right, Monday we will talk about electric field and then we'll get into voltage. Woo!
Calm down.